eV. Ultra-high energy neutrinos are thought to result from collisions of the expanding fireball with its surrounding medium. So now remember that there's also the afterglow, right? We didn't talk about that yet in terms of the neutrinos. Basically, the same kind of collisions that were happening inside the fireball, that's the prompt emission, and that gives us the prompt emission type of photons, protons, and neutrinos. What about the expanding fireball colliding with the surrounding medium? That also leads to certain shocks and collisions and things like that, and we will see what happens there. So, inserting equation 5.2.1. Now, what did I do there? Oh, I see. So, equation, where is 5.2.1? Which equation am I talking about? Who wrote this? Who wrote this? Did I even number my equation correctly? Oh, you know what? It's just that energy equation. It's okay, whatever. Doesn't matter. So basically that same kind of math that we just did for the prompt emission photon and proton, we're gonna do for the afterglow. So a typical afterglow photon energy. So that same energy of the photon that we had assumed to be around an MeV for the prompt emission, because the prompt is gonna be more energetic. We're saying that a typical afterglow photon energy is around 100 eV, and the Lorentz factor is still 100. Neutrino energies of order 10 to the 18 eV are found. Because basically in that energy, remember, it's basically energy of a gamma or energy of a photon times an energy of a proton is equal to some stuff, right? So if the some stuff is about the same, then basically the energy of the photon and the energy of the neutrino are kind of like oppositely related. Like in the parts of the gamma ray burst where you would get more energetic photon, you're supposed to get less energetic neutrino. And if you have less energetic photon, you should get higher energy neutrinos. So this was my point, which is that we don't generally look for ultra high energy neutrinos, or sorry, high energy neutrinos even from the afterglow of a gamma ray burst typically, but we should. I was basically proposing that we design a search for ultra high energy neutrinos utilizing the afterglow. I'll be right back. I ordered sushi. That sounds good. I kind of want some sushi now. So we'll continue. Ultra high energy neutrinos are thought to result from collisions of the expanding fireball with its surrounding medium. Inserting an equation, which we just talked about, that energy equation, the product of the two energy photon times proton energy thing. Because remember, the energy of the photon times the energy of the proton equal to some stuff is important because the neutrino inherits the proton's energy. Remember how we said that if you spread the energy among the neutrinos are about equally, the energy of the neutrino is going to be around 5% of the proton's energy. So as soon as you kind of know the shock accelerated proton's energy in the gamma ray burst, you have an idea for the neutrino that you should be expecting from that particular proton, because we know that that proton, after doing some business, will eventually produce neutrinos, because the stuff that energetic proton will produce upon interaction with the photon, all that stuff is unstable and it's going to decay. And the ultimate product of those decays are all going to be neutrinos. So as soon as you know the proton energy and you have an idea for the photon energy, because you have observations of the photon energy, because that's how we generally historically picked up on gamma ray bursts. It's the photons that we see from the gamma ray bursts, right? The light energy. When you insert all that in the equation, you might get an estimate for the proton energy. And as soon as you do that, you also get your neutrino energy estimate. So I feel like that's so interesting, because the neutrinos, which are also leptons, are not coming from the leptonic tree way of getting